Recording in progress.
All right, guys, welcome to another session of this case kernel pack training, the training for June. So welcome. On this case, we are gonna. I'm gonna show you actually what's kernel drivers, software drivers for kernel. I'm gonna show you a little bit of kernel pack, of course, and also the basics of how to develop a rootkit. And yeah, for that we have to go first through the basics of Windows architecture. Maybe you have already some understanding of how this works. We're gonna use sysinternals to look at some of these details. Sysinternals is a suite from Microsoft that you can download for free. Then we will use Visual Studio to look at a basic rootkit. And then using that rootkit, you will understand a little bit more how it works, uh, how can we interact with it. Of course, I'm gonna encourage you to create your own rootkit so you can start learning it a bit more. Besides that, of course, I'm gonna show you kernel pack. Uh, that is our take on rootkits for Windows and in the future also for Linux and Mac OS X. Okay, so let's dig in. So of course, this is gonna be just a quick disclaimer. This is gonna be a quick introduction to it. It's not going to be a full trading, of course. And so don't expect to learn everything on this hour. We might take more than 1 hour on this training because it's a lot to digest. But just have that in consideration. In the future, if you have any questions about this training and the way we do trainings, please give us the feedback on the community chat we have on Discord. So that will be amazing. All right, so let's begin. Again, the person that's speaking is Juan Saco from XPlay Pack, and the topic for this training is kernel rootkits. Uh, of course, we are basing this presentation on kernel pack in some level. So let's begin. Windows architecture. You might have seen some of this, and also some of the stuff that you see on the screen might be deprecated or might not be there, but the structure still remains. So we have on the top the user mode with all the subsystems. Those are the DLLs. Then we have the critical services that are running on any Windows installation. And then we have the session manager, the WinLogon, the LSAS that you might hear about this process because of Mimikatz, for example, and of course the service control manager where you have the services running. Then lower to it, how do we interact with the part of with the lower part that belongs to the kernel mode? So everything that I said just now belongs to user mode. So how do we interact with it through the subsystem DLLs that after that they interact with NT DLL. NT stands for native. That's why it's native DLL, the dynamic library. And then the NTDLL, so is the lowest part of the user interaction through user mode. Then it will go to the kernel side of it. Then in the kernel side of it, I think here we are well on this graphic is from this PowerPoint presentation is actually from Microsoft, but the kernel is divided into the upper section and the lower section. On the upper section is not here, but I'm just telling you, the upper section is for the executive part of it, and you will see all of that when we go into Visual Studio and we start coding some cool stuff. And then the lower part is gonna be what it here says, the interruptions, the DML, memory, cache control, etc. So then we also have the hardware abstraction layer, and something that we are missing here is the virtualization part of it. So it's and also there is running the part of the secure kernel, right? On the kernel itself, we have, of course, the Windows user GDI, the graphics driver, all the file system cache, the object manager, plug and play manager, and so on, right? So the processes, threads, and virtual memory, local procedure, and the devices and file system drivers. So here's where we're gonna go right now, because we're gonna create a software driver, and it's not gonna be a hardware driver, it's gonna be a software driver. So we're gonna interact mostly with the upper part of the kernel. And by the way, the kernel is NTOS kernel. So that's the name of the binary. We will see it later when we use sysinternals. And here is the kernel architecture. So you see that we have user mode with the NT API stubs here from NTDLL. So this is still on user mode. And then, well, here's on the upper part of it, we have the traffic section, interruption and dispatcher, the CPU management that handles the scheduling and synchronization and all the interruptions and so on. And then in the kernel mode, we have the drivers, the bytes, filters, volumes, networking, graphics, so etc. And it, of course, it handles all of this that I just mentioned in the other PPT. So it's the virtual memory, the process and threads, object manager, security, registry, caching. So that's why it says NTOS executive layer, right? Then below that, we have the abstraction layer for the hardware. And I think that should be it for the architecture, what I wanted to show you. So we will see all of this. For example, just let me just begin by showing you here in Sys internals. Where do we have it? Here. So we're gonna open a Process Explorer. And here, if you look at sysinternals, you will see that NT is somewhere there. Well, you have to run it as just like that, as admin. And then you can see a bunch more of it. So, and I have already added some flags, some properties to Process Explorer. So one of it is like if I go to the columns, I have selected the protection. So it shows me also the protection and the username. So you can see that there are some processes that are running with different type of protections. But in any case, all of this, the highest process is running with system, right? And let's not mix the protections with the usernames, but so that should be enough. Remember, we only have an hour, so I'm trying to give you as little information as possible. So then we have the process system that is running always with the same PID, that is PID 4. And how do we handle this access? Is by using tokens. So this process will have a token, and the process itself is basically a property of the process. So we call it process, but in reality, what is running is a thread. So the process itself, if we look at the process here, you will see that it shows you the thread that is part of the kernel. So it's coming from here. And then if we look at the image, we can already see some part of it. Um, how can we know more about the process structure? If by using, for example, WinDBG, that is the Windows uh, debugger, and then you can do some cool stuff with it, like attaching to the kernel, and you can attach locally or remotely. You can do it through a serial or you can do it through Ethernet. I would recommend you to start learning by doing it local because you cannot get you can not do any damage if you do it locally. But of course, you cannot stop the execution or properly debug your kernel. If you want to do it properly, then you have to use a serial connection between, for example, two real machines or two virtual machines. Or you can choose use Ethernet that is a little bit faster, of course, and then you will have the same result. And of course, you need two machines. But you can start with local. Yes. And then from here, you will have the kernel debugger, that's LKD. And then from here, you can start messing around the process structure, starting to learn how a list entry works, and so on. You can start from there, digging a little bit deeper into it. But basically, what are we gonna do now is to create a software driver, and the software driver is gonna run in the kernel. And as I should show you, the main difference between running from user mode and the kernel is that the kernel have access to everything, and the kernel has no protections. Well, it has some the kernel doesn't protect itself, right? So it can be that some other drivers or there are some management stuff that, like for example, patchgar, that it will try to check for what is happening in the kernel, and that's important because it only checks every now and then. So you don't know exactly when, but that's how patchgar works. And if you want to learn anything more about some of the things that I'm saying, just open a notepad and write yourself patchgar and how it works, and then you can dig a little bit deeper. Or you can remember, you can also go to our community chat and ask me or anyone else, and we'll try to help you if you have any questions. But of course, because we have only 1 hour and we already spent 15 minutes, yeah, I can go only so deep. So what you're saying that if you are in user mode, you have antiviruses, you have EDRs, you have events. There are a lot of stuff that will try to hook you up to detect what you are doing. It will try to detect behavior. It will try to detect heuristics. It will try to detect a lot of stuff in the user mode. And how it works is by just starting hooking everything before it goes into the kernel. Um, Mostly, right? There are other ways, or just like I mentioned, all your actions might be logged, or if they are not, if it's happening in a healthy system, your actions will be logged, will be traced, and then based on those logs and traces, your actions could be flagged, right? So that's a way of making it super simple and super basic on how a detection works in user mode. In kernel mode is a little bit different because the kernel cannot defend itself. So it doesn't have the ability, doesn't at least at least 2025. There is no way of the kernel at this point to be able to detect itself, to detect something malicious happening on it, or trace it. I mean, in the same way that is happening in user mode. So how it basically work in a nutshell, the detections on kernel, at least from PatchGuard, is that it will check some of malicious functions that let's call it that way. It goes a little bit more complex as you might imagine, but it will check every now and then. So you don't know when, you don't know how, but it will try to check some stuff. And if you don't use that, then or you bypass it or go around it, or you find a workaround or a different way of doing or achieving the same result, then of course, PatchGuard will not be able to see what you are doing. Or another way to bypass PatchGuard because you don't know when PatchGuard is gonna check for that action is that you can choose do the action, clean up, and then go on with your rootkit life, right? So that's in the most simplistic way. I might do another training specifically on kernel detections, bypasses, and exploits. Uh, so we can go a little bit deeper on that, but we will see about it. All right, so let's go back. And of course, guys, in the meantime, if you have any questions, I know I'm trying to make it as simple as possible, but sometimes making it too simple is sometimes it's even confusing. So please unmute yourself if you have any questions, or drop it in the chat. I will try to see if I can check on the chat every now and then. But let's start with the basic rootkit. Okay, so of course, what you need is the Windows DDK, so Windows Development Kit from Microsoft, Visual Studio, and then you can start writing your own, well, not rootkits, but you're going to start writing your own drivers, right? So what we are doing here is we are creating a software driver that I'm going to add to the kernel. Somehow we'll talk you about a little bit later on how we can add a driver to the kernel. And the rootkit name comes from the word root and kit, of course, because back in the day, we are talking Unix time, like in the 90s, malicious user, or just simple users were adding drivers into the Unix kernel and finding ways to just get access to the root user from the kernel without having to remember, for example, a password. That could be a way. Oh, I installed this driver into, or well, in the case of Unix, it will be module, and then you will add it into the kernel, and then you could use that in the case that you forgot your root password, right? But we are using it for malicious purposes. In this case, simulated malicious purposes, of course. And then we will use it to have access to the kernel. Why do we want to have access to the kernel? Because after you are part of the kernel, then it's game over. The AB, because the AB is going to be running on user mode. There is no antivirus that runs on kernel mode. So nothing will be able to detect you once you are part of the kernel. And you are on the highest place of the food chain. As I was showing you, you have PS protected signer of part of these binaries that are running a system. This is one of the highest, and then you have the four. So it is a signed process, SMSS or CSRSS or Windows init. So it is signed and running a system, and the kernel runs on top of it, of course, because it is the kernel. All right. So you have, I have here a driver, the most simple driver and also I added a lot of a lot of comments to this driver, so it's easier to understand. And then I also created a user mode application here, and this user mode application is made in such a way that we'll be able to interact with the driver. You cannot interact with the driver. I mean, you cannot just interact with the driver. There are ways of interacting with kernel drivers. You cannot just go and create an application that will interact with it. You have to do some stuff. There are several ways of interacting with kernel drivers. One way, and the most simple way, is by using IO control codes, basically IO CTLs, and that's what we're gonna use. And this, so it's the most simple way. And then you have to share the same structure between the driver and the user mode application. The user mode application is going to run as user, and this is the driver that you're going to load into the kernel. Yeah, so let's start with this one. So here, what I have done, I'm calling NTAEFS, NTDDK, so I can start interacting and creating the driver. As I just said, is DDK is from driver development kit, and NT stands from native. And then here I'm using these undocumented libraries that are coming from NTOS from the kernel itself. These undocumented libraries, meaning that if you look at those, there will be no documentation because they are part of the kernel from Microsoft. So as a user, you shouldn't be calling this, right? There's plenty information online, plenty of the documentation, but Microsoft doesn't want you to use them. But of course, you can still call them, and this is how you called it. It's just like basically when you are creating a DLL, you call extern C, and then you tell where it's coming from. That's why we have these libraries, and then says, okay, NT kernel API, NT status, and then the function. And of course, how we gonna, the properties that it's needed for that function. We are gonna use input output create driver, and it's not strictly required to do it this way, but we also gonna use copy virtual memory so we can use our buffer and then move memory along processes. Because on this particular rootkit, the only thing that we're gonna do is gonna check a process and then gonna read some memory from the process and then change something and write back into it. So let me go ahead and explain it. So here I'm creating the IOCTLs, setting up the driver. You don't have to code it this way. I'm just using namespaces, but you don't have to. This is my way, but you can do it your way. So this is on C++, so you can just do it directly. But well, is better with, I think it's better with namespaces. Okay, so I'm creating, as I just mentioned, I created three functions: attach, read, and write memory. For that, I'm creating these CTL codes. So that's the way that I'm gonna switch between the codes. So I have to assign a code. It could be any other number, but I choose say 65, 67, 777, and then I have attach, so I can attach to the process, read memory, and then of course then this choose the code of it, and then read memory, write memory, and that's it. But this is choose the code of the function, right? Then I have the structure that I'm gonna share between the user mode and the kernel mode application with the driver and the user mode application. So this is the request I'm gonna use, and then I'm gonna share the handle. That's gonna be the target PID, target address, buffer address, the size. You have to have the size and the return size. And remember, when we are coding a driver, you cannot have any warnings of errors. So when you compile your driver, yeah, you have to disable errors or have your code perfect, because otherwise, what's going to happen is that you get a blue screen, right? Okay. But in any case, any warning is going to be marked as an error when you're writing a driver. So then for IOCTL communication, we're gonna have create IO, close IO, and then the device control. We can use device control or we can use write. Well, I'm choosing to use device control. This is device IO. And then here I created the IO RP. It's basically for exchanging the request packages. And this, as I mentioned, this is going to be the structure for the request. So I'm going to first create one, close one, and then write that. And so this is what's going to be sent back and forth between the driver and the application. This is going to be the structure that I'm going to use. And depending what I'm going to be sending, it's going to be read memory, write memory, or attach, right? So any of these three functions. In this case, I'll choose the codes, but you will see those later. All right. So device control, and then here what I'm doing, because I'm not calling device object, and I'm going quite fast, of course, on this explanation, because again we only have an hour, or maybe a little bit more, but not much. So we cannot choose in the kernel. We cannot just leave stuff hanging up. So because device object we're not going to be using, we're just going to use the ERP, the package ERP. So we're not going to use the device object, so you have to directly unreference that, the device object. Even the device control function, those call for device object, but we have to unreference it, because otherwise it will hang in memory, and the only time that is going to be unreferenced is going to be after you reboot your machine. So you have to automatically unreference that parameter if you are not using. You cannot choose leave it. Um, then I'm using KD print X. As you see, it's X because it's coming from the executive, and you will see that a lot where that function is coming from the nomenclature of the function name. And then, well, I'm just saying device control call, empty status, so I can get a status. In this case, first I'm saying, okay, unsuccessful, because then later on I'm gonna call for the status. Then I'm determining the type of code that I'm gonna be passing through the IOCTL. In this case, I'm just setting this up to stack ERP, and IO get current ERP stack location is gonna get the code itself. And then, well, you can do it differently, but I'm just doing it here through a cast, and then getting the accessing the request object from it. Then I'm creating a new structure, because this is the structure that I'm gonna use to glue the process that we're gonna attach into, so we can have it as in structure. And remember, we are not getting the process; we are getting the structure of the process into a P process, right? Then we're gonna check if the request is null. That's it, and then we get get the control code in the stack ERP. And then based on the control code that we got here, so we get the control code based from the user mode application, and then we switch between control codes. That, remember, the control codes are gonna be attach, read, write. The first one is gonna be if target process different null, then we're gonna attach it, right? So we're gonna call attach, and then we're gonna look for the process by ID. I'm gonna check it. Then read memory, then we're gonna use a different function. Yeah, and to read the memory from that, we're gonna use copy virtual memory. That was one of the undocumented functions from the kernel. And then we're gonna read the memory, and then we're gonna use the same function to copy memory. So to write memory on that process. But in this case, we already have the process because we got the process from PS lookup process by ID. By ID. So we got the PID, then we write into that process memory, and you can read memory from a process directly from the kernels. That, for example, you can use this to read the memory from LSAS, for example. Remember, we have here is running LSAS, and it's running a system, and you can choose dump the memory from it. So if you want to have the memory from LSAS, then you can use, if you have kernel access, you can do it. Well, then we check if the IO was unsupported, otherwise we continue. Then this is again optional, a way to unload that driver. And then of course, the driver unload, expect a driver object, of course, but it's gonna be the driver that we're gonna delete from the list of drivers. And then we choose run it and see if it's gonna be unloaded or not. Then here's the main function. So the main function in a driver is called driver entry. Yeah, and again, we are not using registry path on the driver entry, so that's why we automatically unreference that one. Okay, this let me quickly go through this one, and we are almost there. So empty status, again, we check the status failed. So we set the status to fail, so we can check if later on the status. Then we check if it's Windows 64. If it's Windows 64, if it's not Windows 64, then we said 32 bits is not supported, and this is KD print X. So that's a way of printing. KD stands for kernel debugger print, and then X from executive, and then these messages we're not gonna we're gonna be seen is those messages are going to be seen in the debugger. So you have to be attached to the kernel while this driver is running in order to see the debugger. Otherwise, another cool way of looking at those, you can run, as admin, you can run a debug view and then go to capture and select enable verbose kernel output and capture kernel, and then you can see from here what's happening with the kernel. And if you have any kernel debugger, any kernel debug message popping up, then you will see it from here as well. But remember that this is gonna be only shown if you compile it as debug. If you compile it as release, then it's not gonna work. Well, the debug, of course, the debug messages. Next, again, a new debug message, rootkit loading from the kernel, and then we create our so the drivers, when you add it to your kernel, they will have first the device path where it's gonna be, and then of course a symlink that you can access. So you will access the symlink in order to get to the device path. And how you can see those? Again, using Win internals. If you use Windows Object Explorer running as admin, again here, for example, I can see under driver, I can see all the drivers that I have loaded into this virtual machine. And if I go to global, I can see all the symbolic links. So for each driver, for example, TDX, there will be a symbolic link here, right, at some point. And not all the symbolic links are going to be found because some of these links, they will have no target or they have no name. Sometime in this case, we will have a name and we will have a symbolic link name, and it's on the top for this one. So the device path is going to be device rootkit. So we have to say give the full path. It's going to be / device, and then the symbolic link is going to be // this is for global, and then rootkit. Okay. So next, this is how we are setting those up. And then we create we call IO create device, so we can create the device. So IO create device is gonna create our driver object, and then it's gonna set the driver object into the kernel. And then after that, right after that, we can use the symbolic link pass the device path, and then we're gonna create using the symbol linking that the device path. We're gonna create our symbolic link that you can see later on when we load this driver. You will see it here created. If it's not, if you don't have the driver and the symbolic link, there something went wrong, and of course you can use your debugging messages to look at any errors, or you can use the kernel debugger and use breakpoints. Okay. Then here we're gonna set a flag so we can send data between user mode and kernel mode. That's what we are setting this flag. That's why we set buffer IO. And then here we're gonna start setting up our measure functions again based on the functions that we're gonna use. In this case, gonna be create IO, close IO, device control to write into it, and then driver unload. So these are gonna be our functions: create IO, close IO, device control, and then of course driver unload. If I click on it, then you will see what we are good at, and I just explain it those. Okay, next, device initializing is complete, and then after that we clear the flag because we are not using it anymore. We drop a message saying drive initialized successfully, and then after that we return a status. If something failed during the initialization, then we choose delete the device. Right? And that's it. That's it for the driver. This is just a quick and simple driver. And then gonna see, I'm gonna show you the main mode. That was this driver. And then if I go to main mode, remember this driver will allow us to get a process by ID, and then it's gonna use PS lookup, process lookup for that, and then it's gonna. So this is what it's gonna do. So based on the IOCTLs, it's gonna first let us attach to a process, find a process by ID, and then attach to that process, and then get the virtual memory from that process, and then it's gonna let us write into that virtual memory. All right. So that's the driver part. And then if we go to the user mode part of this rootkit, then I'm going to be using get process ID, get module base. I think you might hear about these functions because they are quite normal to use. But basically, get process by ID. What it's gonna do is gonna use TL help 32. That's basically is gonna call create tool help 32 snapshot. It's gonna create a snapshot of the processes, and then it's gonna go through all the processes and based by name, and then it's gonna check if the process name is there, and if the process the process name that you sent to get processed by ID is there, then it's gonna return the process ID, right? So that's it. So basically, what it's gonna do is gonna get this list. We're gonna use as an input, for example, I don't know, uh, process explorer.exe, process xp.exe, and then it's gonna go through the whole list, to all this list, and it's gonna check for each one if the process name that we gave is equals to our input. Then it's gonna return for that one based on the snapshot that he took the PID, the process ID. And then we're gonna do the same, but in this case, instead of doing that, we're gonna check for the DLLs. And so again, using create tool snapshot. But as you can see, we are looking for modules in this case. So it's basically the same, but I can show you here. It's gonna also check for the modules. So here we're gonna check for I don't know, for a process ID. So it's ask for a process ID, and it's gonna check for all the modules. So in the case of our example, we say process explorer. So we got the PID, the process ID, using this function, get process by ID, and then we serve to get module base the process ID, and then we also ask for the module name, and then it's gonna give us the module name based on the module name that we use as input, right? And then it's gonna tell us, for example, CD. Well, this one is always gonna be there, but I don't know. So XML it's gonna be there. Then if it's there, then it's gonna give us the module base. That's why we return the module base here and after the cast. All right. So that's why we are using first and next, and here we're using process 32 next. So those are functions. All right. Then that's it for these two functions. So get process ID and get module base. So remember we are in the user mode. And then we go to the driver. Remember I say we share the same structure. We are using namespace, so we can call it like this. Um, you don't have to use namespace, but it is allowed. So if you wanted to choose do it in a different way, you can. But it looks prettier and easier with using namespaces. All right, so we have these three, the same structure, the same CTLs, the same codes. So IO touch, IO read memory, IO write memory, and then of course, we have to have the same IOCTL codes that we had on the driver, right? Um, Then the structure, it has to be the same, of course, because this is going to be the structure for the requests that we're going to be sending back and forth through these request packages. And so you have to use the same structure. If you use a different structure, it's not going to work. So it's the same structure. And then here we start calling, in this case, first is going to be calling attach process. Well, not here, but later on, I'm just explaining you how attach process works. So this is attach process, and then it specs a handle and the PID that we will have it, of course. And then we say, okay, initialize the request. In this case, we don't initialize it, so it uses less CPU cycles, but you can initialize it if you wanted. But we are hackers, so we don't do it. And then we get the PID, we cast it from the handle, the PID, and then the result is going to be a call to device IO control, where we serve the driver handle that we have, of course, because the driver handle is the one that we're going to get somewhere there. And then we call in this case, because it's attach process, we're gonna call the attach, the IOCTL attach, and then the necessary arguments for the function. Then we have read memory that is basically the same. Write memory is basically the same. We are changing, remember, the read memory and write memory. And if we go back to the driver, the change from here is going to be that attach is going to use PS lookup by process ID, and then read memory and write memory. I mean, remember, this is driver part, kernel side. So it's going to be copy virtual memory and copy virtual memory to write and read. So, and this is how it is implemented. Then we go to the main, because remember we are in user mode. So we do have a main function. We are almost there. So this is quite simple. On this case, we say, okay, user mode rootkit client, we are using a standard cout. So we can do a print in the screen. and then we say, okay, PID get process by ID. We call get process by ID, and in this case, we are gonna use cs2.exe because this is an example for a cheat for Counter-Strike 2. And okay, then we get the process on the PID, and then based on that, if the process, if we get the process or not, we print a message on the screen. Then we create the handle. That's the handle that we are gonna use for these functions. Remember, they of course they ask for the handle, or otherwise you cannot interact with it. And we have to previously know what the handle name is going to be. In this case, it's going to be rootkit because this is for our example. It could be any other handle, and that you can get the handle. Of course, you can get the handle for other objects if you go to global, and then you get here the handles for the symbolic links, and then you can see, okay, what's the handle? It's going to be this, and that, and for us, it's going to be rootkit. Right? When I load it, I will show you here, and it's going to be listed here, device rootkit. So you can look at the handles here as well. What are the names of the handles for each driver? And that doesn't mean that when you cannot interact with any other driver in the system. You can have checks. For example, is the application, the user mode application signed, or it has all these checks and everything is okay? Then I'm gonna let the application interact with the driver, because otherwise you could interact with any driver and tell the driver to do whatever you wanted, right? For example, when I'm running Process Explorer, the Process Explorer is loading a driver, and then I'm interacting with the driver, so I can get all this information that I shouldn't be able to get from a user mode application. So there are some stuff that applications in some cases do. In this case of Process Explorer, it does have a driver that interacts with, but it doesn't mean that I can just go and interact with any driver. The handle interaction with the, I mean, the part that you use to interact with the when you try to create a handle with a driver. Yeah, it's not like that. So we interact by creating a file. So we create this file with the handle, and then we're gonna use that driver handle based on the routine name. Okay, next, if that failed, then we print okay, fail. Else we say the handle has been found, attaching to the process. And then, well, it's going to proceed to attach to the process, and then it's going to attach to the process using our attach process function that is going to serve the handle here, driver, and the PID that we got here from the get process ID. So the PID is going to be the process ID of cs2.exe, and then it's going to attach to that process, yeah, using that IOCTL. Then it's gonna get what is the module name for client.dll. So after getting the module name for client.dll, well, we're gonna get the base address and everything, so we can interact with it, and we can start writing memory, reading memory and writing memory. So the first thing on this, because remember this is a cheat for CS2, so what it's gonna do is gonna check if we press end, if inside a while true. So if you press end, then it's gonna stop the execution. Then it's gonna check for the local player pound, and it's gonna use read memory. Actually, I should explain it here. So it's gonna use read memory, and then it's gonna read the memory using the driver from client.dll, and it's gonna check for the memory of the local player pawn, that in this case is where is the location of the player, right? So if it finds the location, if we reach the player, then it's gonna continue. Otherwise, it's gonna keep scanning. Check if the player is in air or ground. This is more specific, of course, to this specific cheat. But here is going to check if the player is in the air or ground. It's going to check for a flag inside, again, client DLL module base. It's going to read. It's going to, again, use read memory for that. And then after that, it's gonna again read memory, but in this case, it's gonna be to do a for jump to check if that flag is still there, and then it's gonna do a bunny hop. That's it. So basically, it's gonna use, in this case, we are changing to write memory, and then it's gonna use the handle, um, the client, and of course, it's gonna write this value here, and is what and this is the value that is going to write. This is a hard-coded value because on the case of this game, 65537 stands for reset, and 256 stands for jump. So it's going to reset or jump 2 times. So it gets to do the bunny hop as soon as you press space. So if you keep pressing space, it's gonna jump. So that's how you can do this. You can adapt this code, for example, to dump the memory from Elsa's, or look for something in memory from Elsa's. But I'm gonna show you, because that was for a cheat. I'm gonna show you now quite quickly how we load it with this example, and then I'm gonna show you an example of a rootkit that is gonna steal tokens using exactly the same behavior. But remember, we said we have the process structure, and then inside the process structure we have the list entries, and this inside the list entries we have the tokens. And if we reference the token from one process to another process, then we can steal the token for a process and then change the token of, for example, a process explorer, and then say, okay, process explorer is not running anymore as Juan Saco, but it's going to be running as the user that I took the token from. Because if I alter the process structure of Process Explorer, and I change the reference of the pointer of the token for another process, in this case, of course, what you wanted to do is to use a process ID that you already know, so you don't have to go through all that mess. You can also always use the process ID of 4. That's for system, and system is gonna be always run as system. So that's how a steal token works. But before moving forward, I'm gonna use this application, OS loader, so I can load the rootkit, and you can see it there. So we go to rootkit, here, release, rootkit, register service, and start service. Okay. Now if I go here into Windows Object Explorer and I look for rootkit, you see I have the device loaded into the kernel. Yep. So that's a software driver. And now if I go to global and I look for rootkit, here I have the symbolic link that is pointing into this device. So now I can call it from global, from a user mode application. And if I go to user mode, to the user mode app, here, well, it will not work because it cannot find CS2 program. It's not running. Otherwise, it will be starting the while true and going there. But as you can see, if you look at the right side corner of this virtual machine, I'm running this computer in test mode. That means that when I came here, this is running as inside the advanced option. It's running with debug options here. It's set as debug. So that means that this, or I can use BCD edit to do that and disable the testing. Since Windows 11, I think it was 16,002 build or something like that. You cannot choose load drivers into Windows. So, and this is a huge topic, and it's gonna be taking a much more time. So that's why I'm not gonna cover it today. But if you want to load a driver into Windows kernel, you have 3 options. One is do it manually. You do require to change the computer into test mode, disable the signing the test, the check of the signing of the drivers. So because otherwise, Windows only wants to load drivers that are signed. If they are not signed, you're not gonna be able, because here I just created a driver in this virtual machine. I cannot load it because it's not signed by Microsoft. So that's the option one. Disable the protection or setting the computer in test mode, whatever you wanted to call it, and then you can load the driver. So for that, it requires that you restart the machine. In some cases, a device will require that, but because we are using a rootkit, you don't want to restart the machine, right? So that's why that option is not as attractive to us. Penetration tester or red teamers is not that attractive to us. So the second option will be to actually sign this driver by Microsoft. So you have to go through the whole bureaucracy of signing this driver by Microsoft, but you are using this driver for malicious purposes. So if you are asking Microsoft to sign your rootkit and you're going to use that driver for malicious purposes, in this case, it's going to be to do a red team exercise, a penetration test, or a simulated attack, then you cannot do that, because you also became a malicious actor, right? So you shouldn't be trying to sign your driver. So the third way is by abusing, and that's the way that we are doing, is finding exploits, ways to exploit vulnerable drivers. So you can exploit a vulnerable driver that is already signed by Microsoft, that is running or not running in that computer, load it because it is signed, you can load it, and then you can use the vulnerability of that to either write memory, read memory, or load your yeah, by doing that, loading your driver, right? So implementing the logic so you can load the driver. There are some projects that and the most well-known project that is already doing that is KD Mapper. You can use that project, but this one specifically only use one driver, and I think it was a driver from Intel. Let me check. There are some other implementations of a KD Mapper, but basically the main difference is that instead of using the driver entry, you will have to remove the driver entry and use and you just call it from a different main. And then, of course, if you want to use a different driver, then you have to find your own driver, right? Of your own vulnerability. Okay. All right. So let me show you the other example, and then we go to kernel pack. So this is another project from GitHub. In this one, I'm gonna show you still token. And as you can see, again, we have user mode and well, kernel mode. Well, the driver itself. I'm not gonna go to the whole code as I did with the other one, unless you guys wanted me to. But you can find already the similarities. Of course, it's the same structure. It is a driver. So you have the, well, this doesn't have to be here per se, but you have the device name, the symbolic nickname that you have to use always when you create a driver. In this case, it's going to be using two IOCTLs to interact with the user mode application. You don't have to interact with a user mode application. You can just be a driver and just do your own stuff without interacting with the user mode applications. And there are other ways of interacting with user mode applications, and it doesn't have to always be using IOCTLs. Because as I remember, I mentioned PatchGuard. PatchGuard is gonna check for IOCTL. So if you're doing something funny, it's gonna be now and then checking for that. You can also use it and clean it. or you can, yeah, there are some ways of doing that, but you can use memory. There are some other ways of interacting with user mode applications. It doesn't have to be through IOCTLs, but of course, it's the standard way. That's what I'm showing you this. Okay, then we have structures that we're gonna use. In this case, it's gonna be source PID, destination PID. That's it. That's the structure and the prototypes for driver download on device control. Just remember, it's basically the same. We have missed that one, only get the list entry. And then we have the driver entry. There is a main again, because this is not going to be loaded into an application like KD Mapper. So it directly calls driver entry. And then from here, it's gonna do some basic stuff, and then it's gonna start checking for IO create device, create the symbolic link. So first, it's gonna create the device again, as I said, then symbolic link, and then setting up the measure functions. You say on create, so create close, device control, and driver download. So those are the measure functions for this driver. So those are the functions that are gonna be used. And then we have driver download, create close, I should say. And then the main function for this is gonna be on device control. That is the function that is gonna be using to write stuff from the driver into the kernel. So again, it's gonna be using it's gonna be setting the PIO stack location ARP, so it get it, and then is starting to use two API processes, because remember, this is to the goal of this application is to steal a token from a process to another. So so it's gonna need the main token and the main token and the target token. So then it's gonna get this structure for each of for the target and the main, and then it's gonna call the start the PL list entry, the process list entry for the target and the main, and then same target and current PID. So then it's gonna create a process or change that process token, a new process, I mean. All right, so then it's gonna choose as the other driver, PS process lookup, and then it's gonna get the token from the list, and then it's here, and then it's gonna unlink the list after it's used. And then if you go to here to the user mode application, this case you see, because it is a user mode application, doesn't have to be in C++. In this case, it's made in C#. So it's as you can see here, it's asking for two parameters. So the process PID, specific process PID, and then the command to execute using that process PID, and it's going to execute that process with the PID and the access of that token. So basically, it's going to execute, if you wanted to get a CMD with system rights from the driver, then you can choose to, as I mentioned, select system. So it's gonna get the process, the structure from this PID that's running a system, and then it's gonna use that token from that process with your new with your application. All right. So that's almost it for this part. What I wanted to show you now, I'm gonna stop this one. I'm gonna show you the part of kernel pack. Yes. Kernel pack has much more that I just mentioned. So you have here all these functions. So you can interact with processes, modules, threads, drivers. So you can load, disable, hide. You can do whatever you wanted with drivers, tasks, as again, registry. You can patch stuff. You can inject a shellcode in the always using the rootkit, the driver from kernel pack. You can inject that DLL into a process, hide that DLL. You can use callbacks, remove callbacks, and so on. Do whatever you wanted with files, ports, dump elsas. if you wanted, and disable events, enable events, and so on. And all of this, you can also use AutoExec. And then by using AutoExec, there, you can automate all of this. So how do you use it? First, you run kernel pack, and this is way easier. So it's you choose open kernel pack, go into remote control, rootkit wizard. Of course, you have to accept this disclaimer. Remember, what we are in uncharted territory. We are in kernel, and from using this wizard, you will create a rootkit, a driver, and you are able to use any of these two. We will add much more vulnerable drivers, so you can load it without having to manually reboot the machine or set the machine into test mode. We will use vulnerable drivers. At this point, I have a list of a bunch of them. And the way that you are running this for the face interaction with the machine, I'm also adding previous escalation vulnerabilities, because if you find a vulnerable driver, then you also get a previous escalation. It's not just it's not if you can find a vulnerability in a kernel driver, not the rootkit of kernel pack, but a vulnerable driver from a third-party vendor, then of course you get driver access. By using that, in most of the cases, well, not in most of the cases, but in some cases, you can also abuse of that if you have the access to the functions you need, write and read. Then you can also load your own. You might be able to load your own driver. In this case, we are using these two that are signed, and then we're gonna create it. And prior to that, if you want to avoid detection in the case that you have admin but you have an IP running or something like that, then we can also include the unhooker. So it will unhook everything from user mode prior getting into kernel mode. So it's a little bit trying to hide yourself prior getting access to the kernel, so you don't get stuck there. Okay, so if you want to go for manual load, you can do it. But in this case, I'm going to use gdrb sys. Going to create it here. It's going to be called rootkit kernel pack, just like that, saved. And then I go to that folder. And of course, the rootkit of exploit pack, as you have, you could imagine, it does have C2 functionalities. So it's not only that I can choose interact with the computer, I can interact from it from kernel pack, from this graphical interface. So let me go here. I'm gonna get the rootkit. It is here. Boom. Alrighty. Then I do that. Okay, so now you see kernel pack driver.sys. That's the driver of kernel pack, is a rootkit. And then if you use the rootkit loader, then it's gonna use a different driver. So it's gonna use a different driver, and then by using that driver, it's gonna inject or load our rootkit into the kernel, right? So double click the rootkit loader, and if everything goes correct, fine. In this case, it went. So what happened is that after loading the driver that we selected here, well, I really have here the driver running. It ran it injected the kernel pack driver into the kernel, and now it is running there. If I go there, and you will see, I will just show you in one moment. And then after that, it's running the user mode application kernel pack client.exe. Yeah. And kernel pack client.exe is gonna interact with the driver and with the kernel pack graphical interface. So it's gonna be the application that pivots, that's gonna be in the middle between the driver and the user mode, yeah, and the graphical interface. All right. So let me show you here on Windows Object, or with Object. And now if I look for kernel pack, is there, it's loaded. And if I go to drivers and I look for kernel pack, here is running in this system. Okay, so what can you do here? Well, you can do a bunch of stuff, much more that you probably need. So if I select the this one, I can start by dumping LSAS and get the passwords from LSAS from this machine. But let me just show you an example. So I'm gonna run this CMD. I'm gonna check of this CMD. This new CMD is this one. As you can see, if I close it, look, boom, now it's gone. I'm gonna open it again. There you go. And now this CMD, it is running here, and this is the process ID of this CMD. And if I type, who am I? It says I'm Jay Sacco. So it's 7592. I'm gonna go here, I'm gonna list the processes. There you go. Okay, and we said 7592. We're gonna elevate that one. 7592. We're gonna elevate it to the maximum. So it's this one. And remember, it's running here. Jay Sacco, who am I? I'm gonna go here. I'm gonna say, okay, run this command on our rootkit. Okay, operation succeeded. So now if I look at it, now it's running as system. I have took the token, as I just explained before, to this new process. But remember, I said that processes are what is running is a thread, and what the process, what it is a structure. So look at this. If I create a new process, let me just do that. Let me open Notepad. This is confidential. Let's make it really confidential. So it's gonna be confidential. So what is Notepad? Okay, Notepad is 4532. How do we make it confidential? What we can do, we can hide the process. So we're gonna say 5232. So what it's gonna do here is gonna look for the list entry where the process, the whole list entry of the processes of the system. So and then as you can see, all these processes, they are part of other processes, right? Running the system. So we're gonna go into the process structure of the machine itself, and then we're gonna remove it from the list entry. So it's not gonna be listed in the kernel anymore, the thread of Notepad. So 4532, go. And now look closer here, you see it has disappeared. So now what happens is that this process is not listed anymore in the system, right? So it's not listed at all. So it cannot be found in Process Explorer, or it can also cannot be found in the task manager is not there. If I look for notepad, there is no notepad, right? Okay. And besides that, remember we have a full agent here. I can choose A again, but also give me a screenshot because I want to see what is happening. And all of this can be done automatically and remotely. And you have full kernel access on that computer. There's nothing that can detect you, nothing that can trigger you, and you have full access on the computer. So that's game over. If you get to this point, then your report is done. And the good thing, I have great news for you guys, for everyone that is already on this training. If you don't have kernel pack, we're gonna extend only for you guys for today because we have the lifetime a lifetime promo going on because the anniversary of our company. So we're gonna extend it to you if you don't have a license of kernel pack and you want a lifetime, meaning that get access forever on new releases instead of a yearly access. Reach me out on Discord and we can work something out. But remember to finish. Choose a side note. You have to be careful because you are interacting with kernel. Remember, I just said that this notepad is part of the a process structure, and that process structure now is broken. Broken meaning you cannot find the process listed here uh, under the structure of the process list. So the process list and the list entry for this process structure has been removed from the real process list. So now what happened if I close this process, what is going to trigger is the kernel trying to unlink this process, but the process has been unlinked already. So guess what's going to happen? We're going to get, if I click on the cross, the kernel is going to try to unlink this process notepad, but I unlinked it already. I told him that basically this process has ended, but it hasn't, right? So that's basically how it works. So if I click on it, blue screen. So watch it in live. Boom. Oh, but let me, boom. Yes, there you go. All right, guys. I think that should be it. If you have any questions, now is the time, or I'm gonna try to share the recording for you with you guys. Otherwise, we're gonna see us back yeah in a month from now. Maybe we will try to cover exploits for drivers. Let's see how it goes. Thanks for standing yeah for taking a bit longer, and I hope you have a great weekend. If there is no questions, I'm gonna end the session. And if you want to take the promo, the lifetime for kernel pack, yeah, send me a message. Yes, this of course, even if credential guard is enabled, you are able because you are running on a high level. You are running from the kernel, and you don't have. And there is also a question: does the user needs to have certain privileges, as set the back privileges, to be able to steal a token? Well, you are the kernel, so it doesn't matter. You are interacting with the process itself, with the process structure. Next more question. Will you give us the code, the source code for this driver you are using? Yes, of course. Yes, I can share the code with you guys. All right. Thanks, guys. And I hope you enjoy it.
Record